Hello everybody. So I thought I'd make a video going over the contents we covered in today's lectures. So I'll go over it a bit more quickly because I obviously don't interact as much. But let's see how we get on. Okay. So to start with, let's talk about what we looked at the end of the last lecture. And I think we had a differential equation that looked something like this. Oh, I can't remember the terms. Something along this line. Okay, I think there was an epsilon here. And what we tried to do was we tried to find a boundary layer equation for this. Just give me a second to see if we are indeed recording. Yes, we are. That's good. Right, so we tried to find a boundary layer equation for this. And when we tried to do that, it failed. I think we had something along the lines of this. When we tried to find a boundary layer equation. There might not have been a factor of 2. I can't recall off the top of my head. But we ended up with this, and the problem was that there was no delta. And then after that we went and investigated, we talked about regular singular points, and after we looked at regular singular points we found that this had a regular singular point, and it turned out that we found that the answer to this equation, let's call this star, although they're both the same, it turned out that y twiddled a times t to the 1 plus b times t to the minus 1 over epsilon. So I should make it clear here that epsilon is bigger than 0 and epsilon is a small number. So we ended up with this as our equation from last time, and the problem was that when we were looking at this equation here we had some boundary conditions. Something like this, and the issue was with this boundary condition, and it turned out if we tried to stick 0 into here we had a times 0 plus b times 0 to the minus 1 over epsilon. And now this is asymptotic, so we can be a bit loosey-goosey with some of our terms. So we're going to get a times 0 plus b. And because epsilon is a positive number, here we're going to get infinity. And now the issue is we want this to equal 1. And there is no choice of constants A or B, so this equals 1. So this is impossible. And the issue here is the problem is not well defined. The problem has no solution. It's not that it's difficult that it has no solution, it is a badly posed problem. And the very quick fix we did at the end of last lecture was to go and we said that y of 0 is finite. That's what we said the fix was, but I don't think I really spent any time explaining that. And the reason is, let's go across and let's try, instead of setting this equal to 1, let's see what happens if we change that condition to y of 0 is finite. So if you have a look at this, so y of 0, that's going to be a times 0 plus b times infinity. Okay, so right now this is infinite, right? And the problem is coming from this step. So right now it doesn't satisfy the boundary condition that y of 0 is finite. And let's remind ourselves, and this is the bit that's causing us a problem, and let's remind ourselves of the expression for y of t. So it's, I shouldn't say equals here, I should technically say twiddles. So it's got a t to the 1, b t to the minus 1 over epsilon. And this is the bit that's giving me some problems, this b t to the minus 1 over epsilon. And the idea is we can make that go away if I set b equal to 0. So if b equals 0, we no longer have a singularity. So really we can actually make this be finite. So a times 0 plus b times infinity is finite as a condition. So we can actually turn that into a condition on A and B. So we apply a boundary condition, that's what we're trying to do. We're trying to figure out A or B. So this is finite actually just tells us that B equals 0. So this is how it fixes the problem. So to reiterate, previously we tried to do it with the condition we were given, and there was no choice of A and B. There's nothing I can choose here that is going to make this equal 1. But if I change it to y0 is finite, then there is a choice for A and B. I could set b to equal 0, and the boundary condition is going to work. So that's how it fixes the problem. It's the differential equation with the boundary condition that's wrong. Nothing to do with max asymptotics. Okay, so how does this relate to WKB theory, or WKB method? And well, the way it works is there is another way that we can get boundary layer theory to break. And what we're going to do is we're going to consider this differential equation. So it's going to be epsilon y double dash plus y equals 0. Now let's give some boundary conditions. I'm going to go for y of 0 is 0 and y of 1 equals 1. Okay, so let's try and think about this problem. So to start off with, I noticed that epsilon is multiplied by my highest derivative. So I see here I've got an epsilon in my highest derivative. So this makes me think it's a singular perturbation problem. And that makes me think, okay, I've got to use boundary layer theory. So we'll just start off, we'll say it's a singular perturbation. I quite like white on black, it's quite nice, isn't it? Perturbation problem. Okay. So that makes me think, oh, I should try boundary layer theory, right? So this is the mental gymnastics I'm doing right now. So then afterwards I think, okay, if we're using boundary layer theory, then I should try and figure out if it's on the left or the right. This is a linear equation, so I should be able to do that. And then I try to remind myself, how did we do this? And okay, the way we did it was we said, okay, we have a y double dash with an a of t y dash, a b of t y equals 0, and we look at the a of t, right? And that tells us about it. So if we look at this problem, okay, we don't have a y dash term, but that normally means that I've just got 0 y dash, right? So my a of t in this case is 0, so okay, I can do that. So we have a of t equals 0, and then we try and remind ourselves what that means. And normally you say if a of t is positive, it's on the left hand side. If it's negative, it's on the right hand side. But if it's 0, well, we normally say it's an internal boundary layer if that happens at a point. But this is happening everywhere. Everywhere we're having a of t as 0. So right now, this is confusing. Is it on the left hand side or right hand side? Okay, so we've already kind of hit a stumbling block there, but maybe it's not so bad. Maybe it's okay. Maybe there's a boundary layer on the left hand side. So let's continue with boundary layer theory and let's think about what we do next. So the next thing we normally do is we try and solve for the outer solution. So let's try and solve for the outer solution. Okay, let's try and solve for the outer solution. Okay, that seems perfectly legitimate. In that case, we're going to say, okay, let's go for, and the way we do that is a regular perturbation series. So I'm going to say y outer twiddles y0 plus epsilon y1. Okay, and the way that we've got a nice quick trick, haven't we, to find the leading order term, and that's to go to our original equation and stick in and substitute in epsilon is 0. So if I do that, I end up with 0. So we'll just say 2 leading order. I'm going to have 0 plus y0 equals 0. So really, great. y0 equals 0. Hence, y outer twiddles y naught, so twiddles 0. And then this should be ringing an alarm bell because of something we said at the start of the course. I think it was actually a homework problem, right? So remember, we've got something twiddles 0. Well, we said we cannot be asymptotic to 0. That's not 0 factorial, that's just 0, right? We have an issue here. We can't say that the answer, okay, to leading order the answer is 0. That's impossible because everything else must be smaller than it. So everything else has got to be smaller than a leading order, and you can't be smaller than 0. Or if you ever look at the homework assignment, that would mean that y outer divided by 0, when we take the limit, this would equal 1, going back to the start of the course. So there's no end of problems when you try and think about what it would mean if the leading order term is 0, because there's no end of problems. This is impossible. Okay. So basically everything is broken down. We can't really have an outer solution when we do this. So what is going on? Now thankfully, like with most of the problems in this course, when we see something breaking down, we try and look at the exact answer to try and see what is going on. Okay, so let's try and look at the exact answer. So we've got epsilon y double dash plus y equals 0. And we say to ourselves, is this a constant coefficient differential equation? And yes it is, it's constant coefficient. So that means that we can find the solution. So we're going to get epsilon lambda squared plus 1 equals 0. So we're going to have lambda is going to be minus 1 over epsilon squared. So we've got lambda is plus or minus. We've got a negative sign here, so it's going to be I over epsilon to the half. Now we could immediately say, just like we've done previously, that I've got my two values of lambda. So we could say that y is a e to the I over epsilon a half t plus, I don't know why I've done this in brackets, b e to the minus epsilon over half t. Okay, so we could do that, but this isn't the nicest thing to do. And if you want an exact reason why this isn't nice, is because a and b are constants, but a and b are often complex constants in this case. And it just makes it really messy if you do this. But there is a nice trick, and it actually relates to Euler's formula, which I think we said was this previously. So I'm not going to go through all the mathematics to explain why, but we can use this and this result here to basically say that if lambda is I times, I'm going to use the word omega, then we can write y has been equal to, instead of a, I'm going to use the word c1 times sine of omega t plus c2 times cos of omega t. Okay, so if you get a complex, well, an imaginary lambda, the better thing to do than using these complex exponentials is to just use sine and cos. So in that case, if we match them up, our omega, let me get a yellow pen, our omega here is going to be 1 over epsilon to the half. Sorry, I'm just going to add a plus or minus onto there, just to make it clear. We could always get a plus or minus. So our omega is going to be epsilon to the half, so that means that our y, going back to our original question, is going to be c1 sine of epsilon a half t plus c2 cos of epsilon half t. Okay. So this is what we've got for the exact answer. And now we just need to apply some boundary conditions. So if we just go and remind ourselves what they were. Did I actually write them down? Here we go. We've got y of 0 is 0 and y of 1 is 1. So if we go for y of 0 is 0, that means that we've got c1 sine of 0 plus c2 cos of 0, which is going to be c2 equals 0. So that means that my c2 dies, that is 0, so let's just go to the equation here. So c2 is 0, so let's cancel this out. And all we're left with is this c1 sine of epsilon half t term. So let's go this, we're going to go for y of 1, that's going to be c1 sine of epsilon half, and that equals 1, so that means that my c1 is 1 over sine of epsilon half. So hence we've got the final answer, the exact solution. Sine of epsilon half t divided by sine of epsilon half. Okay, so to understand really what's going on, we want to plot it. Okay, so instead of plotting it directly, let's try and get a feel for how to plot this. And let's remind ourselves what happens if we want to plot sine of lambda t. And if we do that, we get something that looks like this. And now we can actually figure out the length of this curve. We're going to call it t. And this happens when we have lambda times t equals 2 pi. So t, the period of the wave, is going to be 2 pi over lambda. So in our case, this is my lambda, this epsilon to the half. So the period of this is going to be t is going to be 2 pi over, sorry, this should be a minus a half there, I think. Just give me a second to go along and have a look. Double check I'm not double bluffing myself. Yeah, it should be minus a half, right? Because it's over epsilon there. So I'm just going to write epsilon to the minus a half there. Okay. So in this case, our lambda is epsilon to the minus a half. So we just end up with 2 pi epsilon to the half. Okay, so the question we should ask ourselves is, what happens if I change epsilon? What happens if we'll start, what happens if epsilon is a small number? Well, if epsilon is small, then my t is going to be small, right? No negative power here. So that means that my period t is going to be a really small number, so we're going to have a small period. So I want to basically do a plot, but my period of my wave is small, and if I try and do that, what we're going to have, let me just go and make a new page. Click onto that. So we're going to have something that looks like this. So there's my axis, and I have lost. Oh, there we go. I can't actually see my marker, so I'm trying to find a starting point. Ah, there we go. I understand why I can't see my marker. Give me 1 second. Let's swap it over to this thing. Okay. So it's a really, really small wavelength. So what this means is I have a really, really compressed sine waves. It looks something like this beautiful piece of work, okay? So this is what the function looks like, okay? So it gets, and as epsilon gets even smaller, right? what's going to happen is we're going to have the same kind of thing again. Let me see if I can draw this plot again very quickly. Go down there. So just to make clear what's going on here, I've done this plot for, let's say, epsilon is 0.1, and if I made epsilon even smaller, right, all it's going to do is going to have this same thing, but it's going to compress it down even more so, right? So we're going to get something even more oscillations. Okay, it's going to be even more. Oscillations. Okay, so this is what's happening in this answer, and what do we expect to happen when we do a boundary layer? So the way I think about a boundary layer, I think let's just go back to our normal example and just draw a plot of it. Normally we have, let's just go down here, and let's go across here. I can't actually see the marker, so that's why I'm struggling to draw these plots. And let's just try and draw it. So normally when we do boundary layer theory, we have, let me go for here. We normally have like an outer solution. It's going to be over there. Actually, just let me undo that and do it by hand instead. So the way we've been doing it previously is we say, okay, I have some sort of outer solution. So I think the one we had previously was something like this. And the differential equation was, I think that's the one we studied. And then we said there was a very, very small region. Let's make this even smaller to make a point. I regret doing this red now. It makes it look like some sort of blood drops. Okay. So there's a really, really small region where our solution changed dramatically. So I'm trying to put a little letter. So there's this little thin sliver, this small region, which we call the boundary layer, and it's in this boundary layer that epsilon has a big effect. And outside of this boundary layer, it has a small effect. Okay. So, what happened in this case? When epsilon changed, was it only a small region that it changed the answer? Well, everywhere, right? So everywhere the oscillations got more rapid. So it changed it for all my values of t. It wasn't a small region, it was everywhere it's exploding. Everywhere it's changing. And we actually have a word for this. We say this is a, I'm using a terminology from Bender and Orszag. We say that this is a global breakdown because everywhere the solution changes dramatically. Okay. And in this instance, because it's only a small bit near zero that it's breaking down, we call this a local breakdown. So really, to get a feel why the problem is failing, is boundary layer theory cannot handle rapid oscillations. And WKB theory came along to sort that out, and it does a really, really good job actually, but there are some limitations we'll talk about next lecture where it doesn't work. But yeah, boundary layer theory doesn't handle these rapid oscillations. And for the next video, I'm going to dive into how we're going to fix this using WKB theory.